All right, welcome to our first of three bonus lessons. We're going to be looking at L'Hopital's rule today. It's a very quick and fast way of doing limits that you couldn't really handle until you knew derivatives, which is interesting since you have to do limits to get to derivatives anyhow. So let's look and see what we have here. First, the hypothesis for L'Hopital, or the situation we have to have, is indeterminate quotients, which we've seen those. 0 over 0 or infinity over infinity. If we have those, we can apply L'Hopital's rule. It says that the limit as x approaches a of f of x over g of x is the same as the first derivative evaluated at a over the first derivative evaluated at a. So if we get indeterminate for our quotient here, we can take the derivative of the top and the bottom, plug in, and we get our limit. So let's see how that works. First, plugging in 0, we would get 0 minus 0 over 0, which is an indeterminate form. So we can take the limit as x approaches 0. Now we take the derivative, and we get derivative of 3x is 3, derivative of sine is cosine, derivative of x is 1, and we get, plug in 0 now, we get 3 minus cosine of 0 is 1 over 1. So we get 2 over 1, which is 2. Easy as that. Looking at our next example here, we plug in 0 again, and we get the square root of 1 is 1 minus 1 over 0 equals 0 over 0 indeterminate form. So we can use L'Hopital, the limit as x approaches 0. All right, so this is, let's rewrite that as 1 plus x to the 1/2. So we get 1/2, 1 plus x to the negative 1/2. Derivative of the inside would be 1, so we don't have to worry about that. Minus 0, derivative of 1 is 0, over derivative of x is 1. So this is 1/2 times 0, no, not 0, times 1, all over 1 to the negative 1/2. So this just comes out to be 1/2. Last example on this page, limit as x approaches 0 of x minus sine x over x cubed. Plug those in, we get 0 minus 0 over 0, which is indeterminate. Take the limit. This is using L'Hopital. Sometimes you may want to mark that. We have 1 minus cosine x over 3x squared. Plugging that in, we get 1 minus 1 over 0, which is indeterminate. Guess what? We can do it again. We're going to apply L'Hopital again. Limit as x approaches 0, we get 0. Derivative of negative cosine would be sine. This becomes 6x. And we get 0 over 0 again. Okay, well, let's try it again. Limit as x approaches 0 of derivative of sine x is cosine x. Derivative of 6x is 6. And we get, plug in 0 here, we get 1 over 6. So we get 1/6. It's quite an easy, or an interesting way to take limits. As long as you have indeterminate form, you can apply the L'Hopital rule. So, what we just did was the stronger form. The limit as x approaches a of f of x gx equals the limit as x approaches a of f prime of a over g prime of, let's use x, sorry, because we haven't taken the limit yet. So we can take the derivative multiple times as long as we get 0 over 0 or infinity over infinity each time. So looking at this, we have square root of 1 minus 1 minus 0 all over 0. That does give us 0, 0, so we can take the derivative. We just did a square root, so I think we can handle that. Again, that was 1/2, 1 plus x to the negative 1/2, minus 0, minus, and then that would be 1/2, all over 2x. So we get 1/2 times this part becomes 1, minus 0, minus 1/2, all over 0. So we get 0, 0. We're going to take the derivative again. So we get 1/2 times negative 1/2 times 1 plus x to the negative 3/2 minus 0 all over 2. Well, this is obviously our last step because we're over 2, not over 0, so we have to stop at this point. We get negative 1/4 minus 0 over 2, so this becomes negative 1/8. Plugging in 0, we get 1 minus 1 over 0 plus 0. That's 0 over 0 in determinate form. We can perform L'Hopital. Taking the derivative of that, so we get the limit as x approaches 0 of 0 minus the derivative cosine was plus, or negative, which minus the negative becomes plus, sine x over 1 plus 2x. Plugging in 0 here, we get 0 plus 0 on top, 1 plus 0 on bottom, so we get 1 over, or 0 over 1, which is not in determinate form, so we have to stop here. But 0 over 1 is okay, we can do that. We can take 0 divided by anything and we get 0. So we actually get 0 for this answer. Here again, we get 0, 0 in determinate form. Perform L'Hopital, we get limit as x approaches 0 of cosine x over 2x. That gives us 1 over 0. We have to stop. It's not indeterminate form. This is infinity or undefined. All right, here's one with some trig. One-sided, approaching from the right. Plug in pi over 2 for both of these. We get, not pi over 2, we get infinity over infinity. So we can perform L'Hopital. Limit as x approaches pi over 2 from the right of the derivative. So we get derivative secant is secant x tangent x. Derivative down here, 1 goes to 0. Derivative tangent is tangent squared x. Sorry, secant squared x. We can cancel out one of the secants, and we're left with limit as x approaches pi over 2 from the right. But we have tangent over secant, so let's write that in sines and cosines. For me, that's easier to see how things cancel out. Multiply both top and bottom by cosine, and we're left with, let's swing it up here, limit as x approaches pi over 2 from the right of sine x. Plugging that in, we get 1. All right, moving on, we get even more functions. We have our natural log function in here now. Plugging in infinity, we would get infinity over infinity. Which one is the bigger infinity? I don't know. Natural log grows slowly, square root of x grows slowly. But let's just take the derivative. Using L'Hopital, remember it's 0 over 0 or infinity over infinity. Derivative, we would get the limit as x approaches infinity of 1 over x over 2 times 1/2 x to the negative 1/2 So let's simplify this just a little bit. I'm going to write this as 1 over the square root of x. So then we do outside over inside, and we would have the limit as x approaches infinity of square root of x over, oh, these cancel as well, over x, which is just the limit as x approaches infinity of 1 over the square root of x, which is 1 over infinity, which is 0. Now, if we have a product that is 0 times infinity or infinity times 0, we can rewrite that to be 0 over 1 over infinity, which is 0 over 0, or infinity over 1 over 0, which is infinity over infinity. So both of those we can rewrite to get into the previous indeterminate forms. But if we see it like this, we have to change it into a quotient, and then we can go from there. So when we plug this in, right here, we get 0 times cotangent of 0 is infinity, so we know this is an indeterminate form. We can rewrite this as x over tangent of x. And now we get 0 over 0. We can perform L'Hopital on it. Derivative of x is 1. Derivative of tangent is secant squared. That's going to be the same as the limit as x approaches 0 of cosine squared x. So now you just plug in and you get 1 squared, which is 1. Super easy. Here we get infinity minus infinity, which is a key that if we combine these fractions, we would get an indeterminate form. So let's do that. Limit as x approaches 0 of these. We'd multiply the left one by x over x and the right one by sine x over sine x. So we would get x minus sine x over x sine x. Now when you plug in 0, you get 0 minus 0 over 0, which is indeterminate form. The limit as x approaches 0, we're going to take the derivative, and we get 1 minus cosine x all over product rule here. The first times derivative of the second plus the second times derivative of the first. Plug in 0, we get 1 minus 1 over 0 plus 0, which is indeterminate. So we're going to take L'Hopital again. Limit as x approaches 0 of 0 plus sine x over, got to do product rule here. So negative x sine x. So the first times derivative of the second plus the second times derivative of the first. And then the derivative of sine is another cosine x. That's going to give us the limit as x approaches 0 of sine x over 2 cosine x minus x sine x. Which when we plug that in with 0, we get 0 over 2 minus 0, which is 0 over 2, which is 0.